So chapter 3 is over the atom. We're going to first look at, like today we're going to look at the structure of an atom, and then we'll look at tomorrow the atomic number, mass number, isotopes, and then we will look at doing some calculations based on the number of atoms and moles. We'll get to using those units and converting. So today, what we're talking about, the first section talks about the theory of the atom, the atomic theory, and how it is different than just a philosophical idea. And because Aristotle actually had a philosophical idea about atoms, but it wasn't really testable. And so what they're showing is the first two statements. Which one is a statement of an opinion and which one's a theory? So which one's a statement of opinion? The first one, and the theory would be the second one, because you can actually test the second one. So same with the difference between Aristotle, and then many, many years later, I didn't change the source. Dalton came up with the atomic theory that was testable. So here are the things we're going to go through in this section. We're going to go through section 1 and 2 today. But we're going to look at the law of conservation of mass, law of definite proportion, and law of multiple proportions. And then Dalton's theory. So, oops. Go back. So chemical reaction is the transformation of a substance or substances to one or more new substances. And it has to follow the law of conservation of mass, where mass is neither created nor destroyed in a chemical reaction. And this is why when we get to chemical equations, why you need to balance equations. You can't lose hydrogen mass, you can't lose carbon mass. There has to be the equal numbers of hydrogen on both the reactant and product side of an equation. And that is all based on the law of conservation of mass. So here would be, here's one of the, this is a chemical reaction. This one wasn't. That's good. Let me make sure you can hear it.
When liquid bromine is added to aluminum foil, the two substances react. Heat and light are indications of a chemical reaction. Aluminum bromide is produced and deposited onto a cooler surface.
Now, all these videos that we'll see are available to you on the website, on the textbook website. I think they're under animations or maybe videos. I don't remember exactly. And then this is the law of conservation of mass.
This law of conservation of mass states that the total amount of matter in a closed system remains constant. In other words, matter cannot be created or destroyed during ordinary chemical reactions. In chemical reactions, such as the combustion of this match inside a closed container, we find that the mass of the starting materials is the same as the mass of the ending materials. The law of conservation of mass explains why we represent chemical reactions as balanced chemical equations. The number of each atom on each side of the equation is conserved, representing that mass is conserved. The law of conservation of mass works for most things you encounter in daily life. In 1905, however, Albert Einstein showed that matter and energy could be equated with his famous E equals mc squared equation. The implication of this is that the law of conservation of mass will not hold for cases where large amounts of matter were converted to energy, such as in nuclear reactions. the law was revised to become the Law of Conservation of Total Mass and Energy.
And one thing that she said in there that was not on the slide, it has to be a closed system. If that, where they showed that match burning, if the lid would have been open, would the masses have been the same? Why not? Right, the gases. When you burn something, you're producing gases, usually some hydrogen gas, some water vapor. That would all escape. So you aren't really violating the conservation of law of conservation of mass. You're just not collecting all the mass products. So that was a good point to make, that it was closed. It has to be a closed system. Okay, and two other laws. It's the law of definite proportion and law of multiple proportions. So law of definite proportions is when a chemical compound contains the same elements in exactly the same proportion by mass, regardless of the size of the sample or source of the compound. Basically it's saying, if you get water, H2O, and distill it from a pond versus water and H2O from the tap water, and you distill it, both sources are both going to be the same percentage of hydrogen and same percentage of oxygen. It's always going to be H2O. It's not going to, one source of water is not going to be H3O, and another source of water being H2O. It's going to be the same no matter what. And then law of multiple proportions, you're comparing two different compounds made up of the same two elements. So carbon monoxide and carbon dioxide, both made up of carbon and oxygen, just in different ratios. And what you're looking at is the ratio of the second element, in this case it's oxygen, with a certain mass to the first element. And that ratio of oxygen between carbon monoxide and carbon dioxide would be a small whole number ratio. So the way you can remember the difference, you're looking at ratios of elements in a compound, but law of definite proportion is within the same compound. So you're looking at the two elements within the same compound, or I guess it could be more than just two elements. And then law of multiple proportions would be you're looking at the elements in two different compounds making up the ratios. The important part of law of multiple proportions is you're looking at two different compounds, but they have to be made up of the same two elements. Or the same three elements. I guess it doesn't matter if it's 2 or 3 or 4. So here is law of definite proportions. I think this is a really good explanation.
Salt, sodium chloride, always consists of 39.34% by mass sodium and 60.66% by mass chlorine, no matter how big the sample is or where it comes from.
It's because it's bonded. The chemical properties change when it's bonded together. Because now the octets have been satisfied.
The salt in the walls of a salt mine might consist of 786.8 tons of sodium and 1,213.2 tons of chlorine, but the proportion is still 39.34% by mass sodium and 60.66% by mass chlorine. A salt shaker with 100 grams of salt would contain 39.34 grams of sodium and 60.66 grams of chlorine. The proportions are still the same. A single grain of salt still contains 39.34% by mass sodium and 60.66% by mass chlorine.
I think that's the end. Okay, so it doesn't matter the size of the sample or where it comes from. And law of multiple proportions.
The law of multiple proportions states that the mass ratio for one of the elements in a compound that combines with a fixed mass of another element can be expressed in small whole numbers. This law can be demonstrated using two compounds formed from hydrogen and oxygen, water and hydrogen peroxide. A 9-gram sample of water results from the reaction of 1 gram of hydrogen gas with 8 grams of oxygen gas. A 17-gram sample of hydrogen peroxide results from the reaction of 1 gram of hydrogen gas with 16 grams of oxygen gas. We note that the amount of hydrogen in both samples is the same. The ratio of the masses of oxygen in these two compounds is 8 to 16, or 1 to 2. From this, we can deduce that there must be twice as much oxygen in hydrogen peroxide as there is in water, and the same relative amount of hydrogen in both. It does not tell us, however, exactly how many atoms of each element make up the molecule. We now know, for example, that both water and hydrogen contain 2 atoms of hydrogen per molecule, a fact we could not deduce from the law of multiple proportions, which simply told us that we had the same relative amount of hydrogen.
Okay. So that's the difference between the law of multiple proportions and the law of definite proportions. So here's just a picture of law of conservation of mass, where it shows the reactions, and you still have two hydrogen atoms here, 1 oxygen atom. You still have the 2 hydrogen and 1 oxygen just rearranged into a new compound. Same with the other 2. The law of multiple proportions, this diagram is showing the difference between nitrogen monoxide and nitrogen dioxide. And when you look at the mass, they are dividing out the masses so that we get it per 1 gram of nitrogen. So for every gram of nitrogen, there's 1.14 grams of oxygen and 2.28 grams of oxygen and nitrogen dioxide. So when you look at the ratio of oxygen between the two, it's a 2 to 1 ratio. So it's a small whole number ratio, 2 to 1. Okay, Dalton's theory. So Dalton was a science teacher in England, and he came up with the first original testable atomic theory. And he said that all matter is composed of extremely small particles called atoms. And a couple of these have been modified, and we'll talk about that. The atoms of a given element are identical in size, mass, and other properties, and they're different in differing elements. Now, the modern theory includes that atoms of a given element are identical in properties, other properties, but they are not identical necessarily in size and mass. You guys know what isotopes are? Heard of isotopes? We'll talk more about isotopes tomorrow, but they are atoms that have the same number of protons, so they're the same element, but they have different numbers of neutrons, which changes the size and mass. Now, the number of protons is what gives it its chemical properties, because it influences the number of electrons. So the chemical properties are the same between isotopes, but their size and mass would be different. So you've heard of carbon-12 and carbon-14, the difference. There's 2 different kinds of carbon. There's actually more than just 2, but those are the most common. So they would be the same, have the same properties, but they have different size and masses. And then atoms cannot be subdivided, created, or destroyed. And we know now that atoms can be subdivided. What are the subatomic particles? Electrons, neutrons, and protons. So they can be divided into the subatomic particles. But if you were to look at a proton from an atom of chlorine and a proton from an atom of sodium, they're exactly the same. So we still say that atoms are the smallest unit of matter that contain the characteristic chemical properties. Created or destroyed, I guess you could just, I don't know that you're, depends on what you think of as created or destroyed. Because on Channel 1, remember they said that they just created element 115? Well, what they're doing is taking 2 atoms and they're a particle accelerator. Have you guys heard of particle accelerators? They're big giant tubes that they accelerate tiny particles through, and there's one in Chicago. And they take them around this huge track, and it's like miles wide in diameter, and then they smash them together. They accelerate it so fast they smash them together, and then sometimes they get them to stick. That's basically what they did to make element 115. Once the elements get so big, they just don't stick together very easily. That's why they said it decayed so fast. But if you want to say that you created an atom, that I guess you are creating a new atom, but you're taking two atoms that are already in existence and smashing them together. So it depends on your definition of create. If you're thinking creating mass, no, you can't do that. But if you're saying creating a new atom based on the other two, we could do that. Same with destroyed. When, like an atomic bomb, what you're doing is splitting a very heavy atom, it's splitting it, and it's releasing its energy and making two new atoms.
So is it technically a new atom, or is it just a compound of the two put together?
No, it's new atom. Like, you'd be splitting uranium into lead, and like what you'd get left would be lead and another element. Okay, atoms and different elements combine in simple whole number ratios to form chemical compounds. You don't have halves of atoms combining, like you don't have, water is not H2.5O, it's always small whole number ratios. And then in chemical reactions, atoms are combined, separated, or rearranged. So we will learn the different reactions, different kind of like synthesis, decomposition, and displacement reactions, where atoms are combined, separated, or rearranged. So under modern atomic theory, we've actually talked about several of these already, where not all aspects are proven correct, so we know that atoms are divisible into smaller particles, and a given element can have different masses. But all matter is composed of atoms, and the atoms of one element differ in properties from other elements.
You need to write all this down.
I wouldn't write everything down word for word, but it's up to you. You can always get this on Angel. This is on Angel. The slide, now sometimes in physics, when I turn the slides into black and white, so you don't waste all the colored ink, for some reason it deletes some parts of it. I don't do that, but so you might have to fill in a few things, but I would say probably not. I don't delete anything. Okay, we're going to look at the structure of an atom. Even though the two shapes, what two shapes? I don't know. So we'll skip that. That's just a little intro. We're going to look at the scientists that studied the atom and found the electron, neutron, or electron and proton, and some of the properties they found. So an atom, talk to the smallest particle element that retains the chemical properties of that element. The nucleus is a very small region located in the center of the atom, and then the protons and neutrons are located in the nucleus. And you have to have at least one proton in the nucleus. If you had no protons in the nucleus, that wouldn't be an element. Surrounding the nucleus is a region that is filled by electrons, and we call that the electron cloud usually. And then protons, neutrons, and electrons are referred to as subatomic particles. I think both of these were exactly the same. And it just showed where the electron is and proton is and where the nucleus. We should be familiar with that. We're going to skip that one. So some of the properties we should know, you guys should be familiar with the charge. So electrons are negatively charged, protons are positively charged, and neutrons have no charge. The mass number is basically showing you what subatomic particles are contributing to the atom's weight and the mass, and you can see that protons and neutrons contribute, but electrons do not. When you look at the relative mass, look how small 0.0005486 AMU is the mass of an electron compared to 1.007 and 1.008. So it's very small, and it would be, we don't even include the mass of the electron when we look at the mass of the atom as a whole. So the electron was the first to be discovered, and J.J. Thomson, actually he'll be on the next slide, but they were doing experiments with cathode rays, and this is a cathode ray tube, and we will watch a little video, it has it on there. But there's a ray of particles that were traveling from the negative end to the positive end, and they were just flowing through, and what they were doing is putting charged plates next to it and looking at what happens to those particles. And those particles then were named electrons. And J.J. Thomson was looking at this, was doing experiments with them, and was able to measure the charge to mass ratio of an electron. So he was able to see how much mass per charge, or how much charge per mass was an electron with each particle. And then Robert Millikan had an oil drop experiment that measured the charge of the electron. So using those two pieces of data, they are able to determine the mass of an electron, which is very, very small. So here is what a cathode ray tube looks like. This is the cathode ray tube. And there's the anode, which is the positive end. Cathode is the negative end. Here. And then the particles are streaming through there. There is a video, so let's look at the video of the cathode ray tube.
When the cathode and anode of a cathode ray tube are connected to a voltage source, electric current flows through the tube and can be seen as a cathode ray. The cathode ray is made up of electrons. When a positive electric field is placed next to the tube, the path of the electrons moves toward the field. Using the strength of the electric field and the amount of deflection, J.J. Thomson was able to calculate the ratio of the charge of electrons to the mass of electrons. Imagine a baseball player throwing a ball. Like the cathode ray, with no outside influences, the ball goes straight when the baseball player throws it. A strong wind, however, could blow the ball and make it go off course. An outside positive field attracts the electrons in the cathode tube and makes them go off course. If the baseball player threw a lightweight plastic ball instead of a regular baseball, the wind's effect would be even more evident. The mass of the ball is one of the factors that determines the path the ball will take. Similarly, if the wind were stronger and the baseball player used the original ball, the wind's effect would be more evident. The strength of the outside force is one of the factors that determines the path the ball will take. By observing the path of electrons in the cathode tube, Thomson was able to calculate the ratio of charge to mass of an electron.
Okay, and then Millikan, his experiment was different, and why? This is what's called the oil drop experiment. So use droplets of oil.
In Millikan's oil drop experiment, he squirted negatively charged microscopic droplets of oil into a chamber and observed them with a microscope. Voltage applied to metallic plates within the chamber allowed him to create an electric field, which had an effect on the droplets. By adjusting the electric field's strength and direction so that it pushed the droplets against gravity, he could suspend the droplets. By knowing the droplet's mass and the strength of the electric field needed to suspend it, he calculated its charge. Testing several droplets in this way, he found each droplet's charge to be a whole number multiple of 1.602 times 10 to the negative 19 coulombs. This is the charge of an electron.
These guys are crazy that just come up with these experiments. Who would think of doing that? Okay, so with those two scientists' theory or experiments, they came up with the atomic model where the atom is this big sphere that has a positive charge all throughout it, and then there were negatively charged little particles, the electrons, mixed in with it. So Rutherford was studying this and was looking at the positive portion of the atom. And so he had a gold foil experiment, and this experiment led to the discovery of a very dense, packed bundle of matter, which he called the nucleus. And so they were shooting alpha particles, which were positively charged particles, at a piece of gold foil and looking at the results. And we have this. Instead of me explaining it again, she'll explain it. But here is a picture of it where these alpha particles, they're positively charged particles, come and hit this gold foil. It's kind of like aluminum foil, just a piece of gold, a little thinner. But they're positive particles, and they used to think the atom had a positive charge over the whole thing. What happens when a positive charge comes into contact with a positive charge? What? They reflect. They deflect each other. So most of those alpha particles should come back and hit them and come back towards the source. But that didn't happen. Most of them actually went passing through. So that's why I said most of the positive charges must be in this small little nucleus. So most of them went straight through. Only a few of them were deflected. So there was only a little area that had the positive charge. The positive charge were not distributed throughout the atom. It was just in that little small area.
Ernest Rutherford with Hans Geiger and Ernest Marsden discovered the nucleus of the atom using a beam of positively charged alpha particles. They bombarded a sheet of gold foil with a stream of alpha particles. Most of the particles passed straight through the foil. About 1 in 8,000 particles, however, were deflected, sometimes directly back at the source. Rutherford explained these results by hypothesizing that nearly all of the mass of an atom is concentrated in a very small volume called the nucleus. If the nucleus were small, it would be easy to miss. Alpha particles which miss the nucleus are deflected only slightly, if at all. Alpha particles which hit the nucleus are deflected severely.
Okay. And then the neutron was the last to be discovered. Why do you think the neutron would be last? Because it's neutral. It's hard to manipulate it if there's no charge. So we have protons and neutrons, and the atoms are electrically neutral because they have equal numbers of protons and electrons. Until we start dealing with ions, the protons and neutrons are equal. And it just is saying that the proton determines the identity. And the last thing is that when you have all these protons together, all the positive charges in the small area, which if you were to expand an atom so it was as big as a football stadium, like the Memorial Stadium, the nucleus would be the size of a marble in there. That's how small it is compared to the rest of the atom. So it's very small. But when all those positive charges are packed in there like that, usually positive charges repel each other, right? So there's this great deal of force that's holding them together, which is what is released in the atomic bomb, that large force. So that is called the nuclear strong force.
Just the nucleus, the whole thing, even with the electron cloud.
Right. The atom.
Is it solid, or is it not technically solid?
Right. That's the big mystery. Your desk is mostly empty space, but yet it's solid. If then that desk is made up of an atom, which is mostly empty space. Yeah. That's what's mind-boggling.